Good morning, Math HL students. This is our remote lesson 5. And in today's lesson, we're going to start talking about applications of ordinary differential equations. This whole thing is meant as an introduction to differential equations. So I'm going to try to give you a little bit of different types of topics. An application, I'm going to give you kind of like classic application problems. Remember the difference between a general solution and a particular solution. This is, I think, the first differential equation we solved. This was Euler's, right? That's what it was called, Euler's. So now we can say this is what? A second degree homogeneous linear equation, right? With non-constant coefficients. This one in particular is called Euler's. Just because I think in one of the previous lectures I told you what the template was for Euler's equation. So these were the general solutions. This is the particular solutions, and these are some of the general solutions, right? Not all. They're actually kind of like all over the place. All right, so we actually solved this analytically. That's how we got this solution, and then I had to use the computer to graph it. Okay, so this is what the general solutions look like. But some of the general solutions. Okay, so here's the question. So in algebra 1 and 2 or whatever, in other math classes, sometimes you get a function and you know how to graph it because you recognize it as an ellipse or a line or parabola. You know kind of what to look for, like how to read off the information you need from the equation, like the vertex of a parabola or whatever, the center of a circle. But sometimes you get an equation and you don't know how to graph it. It's not a recognizable curve. There's no parent function for it taught in standard algebra classes. So what do? You do a point plot, right? You generate a bunch of values of x, you generate a bunch of values of y, and then you connect the dots. Well, for the first thing you do is you kind of look for some characteristics. You look for places where it's undefined, you look for places where there are asymptotes, you look for intercepts, and then you maybe plot some points and get the function, right? If you know derivatives, you can look for min and max. So you can kind of do the same thing with differential equations. If you're given a differential equation, now this is I just cooked this one up, and it actually, I think it ends up being a linear one, right? If you distribute everything. So it just illustrates a particular thing I wanted to illustrate. But this is a differential equation. It doesn't fit any of the templates we've studied. So the question is, can you study the behavior of the solutions without obtaining a closed form? Without obtaining a closed form solution? And the answer is yes, kind of. Okay, so can we describe what the solutions are like without obtaining an algebraic closed form solution? All right, so this is the process. The first thing you do is ask is for what values of t or y is the derivative equal to 0? Because if the derivative is equal, right, so for what values of t or y is the derivative equal to 0? Because if the derivative is equal to 0, the original function must be a horizontal line in those places, right? So there must be a value of y that just solves, equal to a number that solves this equation. So notice that t does not come into play at all. So the differential equation is just a function of y. The derivative is just a function of y. So we'll ask for what values of y is the derivative 0. Okay, well, this is simple. You can just factor y squared minus y minus 2. So the derivative is 0 when y is 2, right? If y of t is just equal to 2, that's what I mean. If y of t is a function that's equal to 2, you can plug it into here and the derivative is 0. Right, okay. And then you have 0 equals 0. So y equals 2 does solve this differential equation. That's what I meant to say. If y of t equals 1, that will solve this differential equation as well. You'll get 0 equals 0. Y equals negative 1 will solve this differential equation as well. So y of t equals 2, y of t equals 1, and y of t equals -1 are my three solutions. And the derivative, they're flat lines. So instead of drawing flat lines, I'm just going to, you can actually draw flat lines if you want, and I do it on the next line. But I'm going to draw the slopes. So the slope, these red arrows represent the tangent lines drawn at a point to the curve. So you have y of t equals 2, that's a flat line, so the tangent lines are all flat lines as well. Y of t equals 1. Okay, so you came up with three solutions just by asking the question for what values of t or y is the derivative equal to 0. You came up with the solutions, okay? All right, so now the question becomes, what happens in between? What happens in between? Okay, so let's try different values of y. Again, the reason why we're not plugging in t, because the derivative is not a function of y and t, it's the derivative of, it's just a function of y, but you can do this with y and t as well. So let's try let's try a different values of y. All right, so I created a table here, right? And what I did is try some numbers between -2 and -1, between -1 and 1, between -1 and 2, and between and greater than 2. So I tried negative. So when the value of y is -2, the derivative there is 36. So when y is equal to -2, the slope of whatever functions pass through it, right, whatever curves pass through it, is 36. So they're almost vertical in that spot. When the value of y is -1.7, the slope is 21.27, and so on. When the value of y is -1, we know you get a flat line, and I did the rest of them. Okay, so I'm not going to ask you to draw these by hand. I've been in math classes where they ask you to draw direction or slope fields by hand. It is unbelievably tedious. I'll show you an app that does it. But let's say we drew these by hand. And I drew, okay, but let's say we did it, and you basically just use like graphing paper and a ruler and so on. But you drew this by hand, you get something like this. Doesn't this kind of look cool? It looks like undercurrents, right? Undercurrents. Like the surface is smooth, but underneath you get different currents here. All right, so what ends up happening? So at -2, the derivative is 36. So whatever function, whatever curves pass through this, at when y is -2, they have, for all values of t, they have slope of tangent line equal to 32. And then you can kind of pause and compare this to a table. And then at like -0.25, the slopes there is -2.64. So the tangent line is falling at, yeah, can you imagine doing this by hand? What's the difference between -2.81 and -2.64? But okay, and then at 3, the derivative starts getting larger again. All right, and so on. Okay, all right. So, all right. So this is called a direction or a slope field of the differential equation. We've never solved this thing, but what we can do is, and this kind of looks cool too. So you can, so here's my 2, here's my -1. I said we were going to draw lines there eventually. Here's my 1. And then there's infinitely many general solutions for every initial condition, right? I'm going to go back here for a second. It depends on where you start. Okay, so an initial condition is kind of like stepping into a river. It depends on where you step in. A current will take you to a different place. Like it'll follow a different particular solution. So there's infinitely many general solutions because there's infinitely many real numbers, right? So you can draw in a curve, many curves, so that they kind of draw a few, not to crowd the field and just to see the patterns. All right, so here's some general solutions. Okay, and then I did say we're going to study the behavior of the solution. So what's happening here? Okay, so if your initial condition is less than 1, if you stepped into the river on this part, so between -infinity and 1, the current will carry you to y equals -1. So at 2, not including 2, right? Because 2 is its own flat solution. It will actually converge to 1. It will converge to 1, right? So whatever outcome. Okay, so y equals 2, you get a flat line at 2, and then if your initial conditions happen to be greater than 2, then you will be carried to infinity. So your curve will just start getting larger and larger. Okay, well, you must be thinking now, well, these values of 1, 2, and -1 seem to act almost like magnets. They either attract other solutions to themselves, like in case of -1, right? Things to the left and things below and above -1 are attracted to -1 eventually. They either repel them, like 2, it repels the solutions in both directions. Okay. Yeah, this stuff gets interesting. So now you have, if you had nothing between -1 and 2, this would make sense because things get repelled from 2 and attracted to 1, right? But you have something in between 1. So do you see that forces the solution at 1 to both attract and repel? Because below it is it's called a stable solution. We'll talk about the definition in a second. It's something that attracts the solution, and above it is something that it's unstable. What's the opposite of attract? Repels. There we go. Repels solutions. So y equals 1 is an interesting one. If you end up below it, you actually have a nice, well-behaved solution. It kind of looks like a logistic curve. Yeah, you have something going to -1, and anything above it goes to 1. Okay. All right. So these solutions do have a special name. All right. More of ODE stuff you learned in the first few lectures of an ODE course.